Alright everybody, so let's take a look at some applications of trig functions. In actuality, we've actually looked at some of these already. My little picture of the guy looking up into the tree, remember we've started all of this by thinking about the bird up in the tree and trying to find how long of a ladder to get to there. And now we've even used, with some of our recent lab that we've done, trying to, given some angles, we can find some distances using trigonometry as well. So the first part of this, the first couple problems here are going to seem like problems that we've done already, which they are. And then we're going to look at an application with some polygons. So you should have a notes worksheet that's online, which you can download and print. Otherwise, you can just do these problems in your notebook. Should be about like six or seven problems that we're going to do here today. Have your calculator ready and make sure you are in degree mode. All right, so I have a right triangle that I'm going to be dealing with here, and I want to do some calculations here and some labeling. So now on the notes worksheet, I only have one picture of the triangle. You're going to have to make your own triangle for each of the 5 problems and label it ABC. For the vertices, angle C is on the right angle. And so we're saying that angle A is 55 degrees, 55 minutes. And side C is 16. Remember, side C is across from angle C. So here's side C. Side C is 16. I want to find side A. And side A is opposite angle A. Well, looking from the angle that we have here, I want to pick a trig function. So what sides are in play here? A seems to be opposite, and C is hypotenuse. Opposite and hypotenuse may be a good idea to just write SOHCAHTOA at your top of the page. So I think I'm using the sine function. So the sine of 55 degrees, 55 minutes equals A over 16. And just solve for A. So it feels like we've done these already. We have, except now I'm having you label the triangle. So at this point now I need my calculator. Now, we could do one of two things. This is 55 degrees, 55 minutes. So I can convert 55 minutes into degrees as a decimal and then make it 55 point whatever number of degrees. But on my calculator, if you go into the angle menu, which is above the apps button, you're going to see number 1 in the angle menu is the degree symbol, and number 2 is the minute symbol. So you can actually type into your calculator 16, then times the sine of 55, and then go and get the degree symbol from the angle menu, and then 55 minutes, go and get the minutes from the angle menu. And when you do that, you can then calculate and get the answer of around 13.251 is the length of A. I would say at least be rounding to 1 or 2 decimal places. I took it out to 3 in this case. So yeah, we're going to come across some angles that we can just type into our calculator. Again, using the angle menu to use the degree symbol and the minute symbol, or once again, divide 55 by 60 and add that to 55 degrees. Let's take a look at another one. Okay, you got to draw yourself a new triangle. So A is 9. Across from opposite side A, or angle A, side A. B, angle B is 49 degrees. Find side B. So looking from the angle that we've been given, what 2 sides are in play? Opposite and adjacent, OA. Sounds like tangent to me. So the tangent of 49 degrees equals B over 9. And just super simple solving for B, grabbing my calculator, and I get about 10.4-ish. Pretty straightforward. How about you pause here and you label up the triangle. You can turn me back on to see if I've labeled it the same as you, and then maybe pause again to actually try to solve it. So angle B, side C, which is the hypotenuse, and side B is across from angle B. So I'm seeing opposite over hypotenuse looking from 56 degrees, 48 minutes. So opposite over hypotenuse. I get 52.8. Hope you did too. Once again, pause me, label it up. You can unpause and then see if I labeled the same, but then pause and try it again. So in this case, I had to do a little bit of extra work because the variable was in the denominator. So just multiply both sides by a, excuse me, and then divide both sides by the tangent of 64. One last one. Okay, pause, try it on your own, and then we'll compare. So here I'm doing 14 divided by the cosine of 16, and I get about 14.6. Which makes sense. It's a little bit bigger than the other side. Remember, the hypotenuse has to be the longest side in my triangle. Or right triangle, I should say. Okay, so let's look at a relation problem here. So we've got a house, and we've got a ladder leaning against a house. And it makes a 70 degree 5-minute angle with the ground. That's called an angle of elevation. How far up the side of the ladder does up the side of the house does the ladder reach? Well, the other piece of information I forgot to write down is that it's a 30-foot ladder. So what am I trying to solve for? How far up the side of the house does the ladder rise? So I'll call this y because it's going up and down. So I'm looking for this side of the right triangle. So looking from the 70 degree 5-minute angle, which two sides are in play? I got opposite is what I'm trying to find, and hypotenuse is what I have, the 30 feet. So it sounds like I'm doing a sine function. So opposite over hypotenuse. Multiply both sides by 30, and I get it's about 28.2 feet up the wall. What is the horizontal distance between the bottom of the ladder and the wall? Well, that's probably this distance right here, x. Do you know which trig function we're going to use? Well, I'm going to use the cosine. Now, technically, I already now have the value of y, but just in case I made a mistake getting y, let's just use the information that we have. I'm using the angle that I was given and the ladder that I was given. So adjacent over hypotenuse. And again, this should be pretty straightforward. We've done this in the lab. We've done this in some practice problems. And then, so therefore, I get x is about 10.2 feet away from the wall. Pretty easy. All right, so let's finish with an example here that I'm going to have you then do some practice problems beyond this. It's dealing with polygons. So here I have a regular hexagon. Now, a regular hexagon or a regular polygon means all the angles and the sides are equal. So all the angles are equal and all the sides are equal in measure, or congruent, I should say. And it says it has an apothem of 4.6. Well, what is the apothem? Well, wherever the center of this hexagon that's circumscribed by a circle, or the hexagon is inscribed inside the circle, the apothem is the perpendicular distance to a side. That's that distance right there. And that is a distance of 4.8 centimeters. So one question, first of all, here is, what is the radius of the circle? Well, the radius of the circle is measured from the center out to any vertex of the hexagon. That's my radius. And if you look closely, I drew the radius there. There's a lot of places I could draw the radius, but I drew it there. Why? Well, because I get a little right triangle. So off to the side, I'm going to make my right triangle a little bit bigger so I can see it here. So there's the radius on the hypotenuse, 4.8 along this side here, right angle at the bottom. And so for me to know what the radius is, do I have enough of information? It seems like I'm a little short of information. What other information could I figure out? Well, in this regular hexagon, where all the angles on all the sides are the same, let's draw in all the radii just to kind of see what's going on here. What do you notice? Well, I notice I get 6 exactly congruent triangles inside of there. All 6 triangles are exactly the same. Do I know what this little angle is right here, this central angle? Well, all the way around the circle would be 360. But it's broken up into 6 separate triangles, all that are going to be the same. So 360 divided by 6, that's 60 degrees right here. And if that's 60 degrees right here, what is that going to make the little angle inside my triangle right here? Well, that's just going to be half of it, because it's dropped a perpendicular down, so that's just 30 degrees. Now, yes, this is now a 30, 60, 90 triangle, but I can't put the ratios of 1, 2 squared to 3 on here because this obviously has been scaled up because this side has a length of 4.8. Let's just leave it as is here. So now do I have enough information to solve for the radius of the circle? I think I do. So looking from the angle of 30 degrees, so I don't get confused, let's take the 60 out and let's just look from the 30. So looking from the 30, which 2 sides are in play? I get adjacent and hypotenuse, so that sounds like cosine. So the cosine of 30 degrees is 4.8 over r. All right, on your paper, do the multiplication. Multiply both sides by r, divide both sides by cosine of 30, and in the end, see if you get 5.5 centimeters. So part B, what is the length of one of the sides of the hexagon? Well, one of the sides of the hexagon is this whole side right here. But if I can figure out this side on the bottom of my triangle, I'll at least have half of it. I can double it. So I don't know, let's make up a label. Let's call that x. So now what trig function's in play? I got 30 degrees. I'm looking for x. Let's pretend I didn't solve for r yet, but I know 4.8. Which trig function is that going to be? I think I'm getting tangent. Oops. Tangent of 30 degrees is x over 4.8. Grab your calculator, calculate that. And I get 2.25, but that means one of the sides is now double that, so the sides are going to be 5.5 centimeters. All right, so a little right triangle trigonometry going on here. What's my next question? What is the perimeter of the hexagon? Well, again, this is a regular hexagon, so all the sides are the same. So I just found one of the sides. So there's 6 of the sides. So I get 33 centimeters for all the way around. Last part is, what is the area of the whole hexagon? Well, what we'll do here is we'll figure out what is the area of one of these triangles. Let me shade it in here. Let's figure out what the area of this triangle right here is. And then I'm just going to multiply it by 6. So the area of one triangle, area of a triangle is 1/2 the base Well, what was the base of the triangle? That was 5.5. Times the height of the triangle. What was the height of the triangle? Oh, right, that was the apothem. That's 4.8. And I get about 13.2 squared centimeters for the area of one triangle. But the area of the hexagon is going to be 6 times that, because there's 6 congruent triangles. And so in the end, I get about 79.2 centimeters squared. One follow-up question that I'm going to ask on the practice worksheet is, what is then the area of the circle that circumscribes it? Well, I already know the radius. That's the first thing I figured out. So just make sure you remember that the area of a circle is pi r squared. All right. Try the problems on the practice worksheet. They're dealing with a pentagon and a hexagon. Good luck.